I just don't know if I would be able to admit people in the lobby if they enter later on, because I will be presenting, so I will be in presenter mode. So maybe I will wait 1 minute more, and then I will eventually just jump in and see if people join. I will maybe stop 1 second to let them in. Yes, I don't know if I can. Yeah. Yeah, no, it's not good. Yeah. Everyone can bypass the lobby. Yeah, okay. So like this, they should just enter. Let's see if it works. Okay. So I would start anyway. The first part that I had planned was to go 1 second over the assignments for the last, over the comments and assignments of the last lectures, because I noted down last time in the comments there were some of you that are working on 3D models, natural language processing. There was LSTMs for time series, then there's colorization, point clouds, object detection, and image super resolution. And I took like one of the models that was coming out twice. So this one, the interpretability of long short-term memory, so LSTMs and recurrent units. And I just wanted to leave a comment because we didn't have the time to touch this during the class. This was a short course, and it was organized very quickly for the project so that we could start it. We could start giving it right after the start of the project. But eventually, if we're gonna expand this course and make it larger, we could include something related to this. But anyway, I wanted to just touch base on this. And in case you're not familiar with LSTMs or gated recurrent units, so the idea is that these are cells in a recurrent neural network. The recurrent neural network is a network that takes into consideration also an internal state, so keeps track of the state of the information. And these two types of cells have a mechanism that is called gates, and the gates regulate the flow of information. So there are multiple gates and in both of these structures, and the gates control what kind of information is kept and or is thrown away. And in particular, in the LSTM, there is a cell state that acts somehow as a memory, and this memory is kept inside the state of this LSTM and is used to make to then pass to handle the flow of information. So it's passed through activations, and there can be sigmoids or tanh and so on. So an example of this can be, for example, like as I was saying, some applications might be the prediction of time series. So if you have weather patterns or disaster predictions, so for example, I don't know, you want to predict whether it's going to be a flooding, you might want to implement an LSTM network for this kind of data. And as I was mentioning, like in the other assignments, one important thing to think at is who is the receiver for the explanation. So why you might want to generate explanation, what for, and depending on who are the people and what are their tasks and also their level of expertise, but you can generate different types of explanations. So for example, the developers may want to have a look at the details on the data, on the models, on the predictions. We all went through this during classes, but in particular for LSTMs, you might want to look at this attention on input features. So in the memory cell, you might want to have a look at how the memory is acting on the different features, or projecting these on your input data. And you might also want to look in between relationships between this prediction and the input features, or directly take the embeddings of your network, like in the internal state, you just take it and you plot it down, so you can apply some kind of dimensionality reduction, if you want, of the embedding. So I don't know, some UMAP projection or something like this. And this is all from on the developing side, something that helps you understand what the model is doing and how the model is working. If the addressee of the explanation are software owners, but then the kind of information they may be interested into is slightly different. So they might want to know what is it that might cause some faults in your model. They might want to know what is the minimum number of features that they need. If you think about prediction of weather patterns, even the flooding prediction, but if you have sensors that are spread everywhere and each feature is a sensor, you might want to minimize the number of sensors that you need, because you might want to minimize the cost of your tool, of your application. So you might want to remove redundant information, and you might also consider the fact that you might have some sensors that are slightly more accurate than others, or that you trust more than others because of the location or something else. So the software owners might want to check whether these sensors are taken appropriately into account by the model, because if they have a super expensive sensor that is a feature, but this feature is not being used by your model, but then this super expensive sensor put there is it doesn't really have the purpose to exist. So it's a cost for the software, for the people involved in the tech business. And other type of recipes can be, for example, the town hall or the users or companies that care about electricity generation, because they might want to care, like they might care about the prediction that you do of weather patterns. And these kind of people are generally mostly interested in justifications for the model prediction. So if there is a flooding predicted, they want to know, like, on the basis of what, to understand whether this prediction is reliable or not. And I wanted to also point to this paper because I think it's a good start for interpreting LSTM. So it's a lot of work has been done about it for interpreting convolutional neural networks for visual inputs, and less has been done for everything that is related to time series. But there are works on this. It's just they're a bit more difficult to find. And also one thing I wanted to say is that everything, I mean, at the end, it's just a bunch of data. So it's true that the convolutional architecture has a particular structure, so it helps you to develop some methods that are much more specific to the structure itself. But there are several methods that already exist that can also be applied to LSTMs and to recurrent models, and also to, like, fully connected dense layers, for example. So in this paper, essentially, the first thing they're doing is they're training a bunch of RNNs, LSTMs, and gated recurrent units, because they want to. So this was kind of it's a paper that is not that recent, and what they were saying was the performance of the LSTMs and the gated recurrent units always outperform the performance of the recurrent neural network. And why is that? So what they did is they performed the clustering essentially of the prediction accuracies, so the model accuracies of these models, and they really showed that these LSTMs and gated recurrent units really behave similarly. And what I'm showing here is the t-SNE embedding based on the probability assigned to the test set characters. So similar probabilities are given to the test set characters by these models, meaning that they kind of are functionally equivalent, meaning that they act similarly. They give the same prediction for the same character, whereas RNNs form a different separated cluster. So that was the first observation they did. And then they reflected about this LSTM memory cell, the presence of these cells, and they verified here on this experiment on the right, in this figure, whether this cell actually acts in a meaningful way, so if it has a structure. And what they did check was that if you visualize this, the activation, so I don't remember exactly, but I mean, it's a tanh activation. So yeah, so -1 is red, so this is negative activation, and +1 is blue, so this is a positive activation. A tan H has goes from -1 to 1, so it has two double sign activation, and they visualizing the positive and the negative activations, and it seems that this cell has positive activation every time a line starts, like depending on where you are in the line, and this one activates positively when you are inside the quotes. So this is all on qualitative evaluation. They visualize it on the test set, and they kind of did some kind of generalization on top. And it seems that there is some kind of structure in the way, in the patterns of these activations. But this is, again, all qualitative evaluation. So to really make sure that that this is solid and stable, you can start with this, but then you need to go farther on. And this is also what this lecture will be about. It will be about the fact that having only a qualitative assessment of your result might lead you to confirmation bias. So you look at this and you think, oh yeah, it's really turning on inside the quotes, and you're convinced of that, and maybe something else is happening, and that's not really true. It's just that the network is doing what you expect it to be doing, and you think that that is correct because you expect this behavior to be correct. So yeah, as I was saying, another thing to mention is that there are tools that, for example, we didn't touch in this class the Shapley values, but this method is sort of unifies multiple methods, and it's a model agnostic technique. So model agnostic means it doesn't matter what kind of model you are using. What matters is this correlation that I was saying between the input and the output. And by observing the behavior from input perturbation, so feature perturbations in the output, you can still do some kind of interpretability analysis, and this is what they propose for recurrent neural networks and LSTMs and so on. So, for example, there are some examples in the GitHub for sentiment analysis, and this is another one for natural language processing. And essentially, in this example, for example, here they have a model that is predicting the next word, so not anymore the next character, but the next word. And here you have like the sentence that is the input, and I don't know, scientists discovered a herd of unicorns living in A, and then here there are all the predictions, and here there are the feature importance values. So this is the SHAP output is a table that tells you a weight per feature. So each of these is a weight that is given to each feature to predict this word, and another word, and another word, and these are words sorted in terms of probability. So the most probable word, according to this language model, is cave. So in a shocking finding, scientists discovered a herd of unicorns living in a cave. And here you can go and you can look at your highest weighted feature that is, okay, the article before. I think this is trivial. And then there is this in. So this in kind of is telling you maybe that is inside something. And here you have these unicorns living, probably is a trigram or something that is being used here. So yeah, this gives you an idea anyway. It's like each column of this table is one of the features, and here you have the weights given to each of the features by this model, and that's what exists in the literature so far, I think.
How is this one called? This model? This
So this is SHAP. This is
SHAP.
This is yeah. I can show you also on their GitHub. 1 second. I haven't worked with it personally yet. I worked with Lime, but I know that Lime is some kind of a version of SHAP, if you want.
Okay.
But
no, I mean I got it.
yeah.
I wrote it down. No
Yeah.
worries.
Essentially, the idea is really like it used game theory, so that's why I was saying like it's feature perturbations, but it's mostly like it's kind of uses game theory to evaluate the importance of each input feature with respect to the output. So it's more complicated than that, but then it can eventually degenerate if you change some conditions into some kind of perturbation method. So that's That's what I wanted to say. And okay, cool. I saw that some people joined when I started, so it means that joining is working, even if I don't give access. Okay, so I will continue and I will go back to the lecture of today. So the objective today is really to understand and to discuss a bit how you can evaluate the outcomes of your interpretability analysis. And I will adopt this outline to touch these points. So the first thing is really to discuss the motivation and point out why this is really essential. The second point I want to make is that it is important to target the explanation receiver, and I think I've said it a million times, but it's still kind of important because so far a lot of the development has been done mostly to address developers, and not all the people that will receive the explanations are actually comfortable with machine learning theory. They're not developers, so there might be more consideration to take into account. Then I will also have a quick discussion about some ethical concerns and the generation of empty explanations. And this is kind of related to understanding how our human brain works. And I won't go too deep into this, but I think it's still important to see the risks that can be connected to generating explanations. And then I will kind of give a proposition about how to go find a roadway to generating explanations. So starting by adapting rather than applying. So, and I will give an example for medical image analysis because this is what we're specialized in. But I'm sure that it can apply to several other domains. We will then have a look more structured about general metrics that can be used for evaluating explainable AI, and these were really general. So they were given for any type of application, and I will then show and go back again to some examples of evaluations and some things that we could observe since we started evaluating our experiments. So first of all, let's jump into the motivation. So machine learning models are not always transparent in decision making, and we know that deep learning is extremely opaque and perceived as a black box. And the thing is that as with developers, we want to use explainability for reasons like debugging the model, getting insights about the learning mechanics. We want to check for biases in the data, confounding factors, anything that is telling us this model is not working in this case, or anything that is letting us understand a tiny bit how the model is working. When we then move to using this explanation to justify the model predictions, we might fall into the risk of convincing ourselves that the model is working as expected. So the thing is that not all circumstances are equally easy to explain. And this is what the picture here on the right is trying to show. So this is something that really happened. And it's a really funny picture because just this event is really difficult to explain. And it represents all of the circumstances that are not easy to explain. And for developers as well, some applications might be more difficult to explain than others. So depending on the domain, the requirements for your explainability tool need to differ and need to require some tuning. Also, another point is that there is actually no point in generating misleading explanations. So we really don't want to generate explanations that convince us that the model is doing what we expect. We don't want to generate something that convinces us that things are going as they should. We want explanations that let us raise the doubts and that point us to what the model is doing without necessarily convincing us. So evaluating the experiments is a really important part that should drive the development of explainability techniques itself. So you should develop a technique and then evaluate it and then see where it's not working, what is not happening well, and you should see whether you can do any better than what you have already. So this is really a cycle. And again, you should target the explanation receiver. And there is this paper by Adrian Weller it's called Transparency, Motivation, and Challenges. And he identifies 7 types of goals for the interpretability analysis, depending on the receivers. So as I was saying, the developer mostly wants to understand how the system is working because it wants to debug it or to improve it. The users might be different types, and they might want different things. So in one case, they might want to get a sense of what the system is doing and why. And this means that they want to know what the prediction is going to do also in unforeseen circumstances, for example. So something that is out of your distribution, what is the model going to do? And this will let them build a sense of trust in the model. Then it's also to help them get comfortable with the model itself, because it's anyway some kind of, it's called artificial intelligence, but it's been addressed as something that is inhuman intelligence, because it works in a way that is very far from how humans work. So giving them explanations helps them to keep using the system. Then there might be some users that need an explanation because this helps them move into some action. So if you're recommended a song, or if you're recommended a product, maybe like this, I think this happened to everyone. Like you go, you want to buy some product, and they tell you, oh yeah, for your type of, I don't know, for your type of skin, or for your type of job, or for your type of activity, you probably need this. And that is because, I don't know, your skin is sensitive, or your lifestyle is active, or something like that. So giving an explanation pushes you maybe to make a purchase. And you see here that there is a little red flag raising up, because it's like, if I give you an explanation, maybe if I give them an explanation, maybe the user will make the purchase, so maybe I can get benefit from it. If you are obviously the deployer of a system or of a service, of an AI service, for example, in this case, Amazon, gets benefits by suggesting products. And another point is auditing the system. So the user might want to audit the system to establish whether this system is actually reliable. It actually it can help to build a sense of trust. And even in case of trial, and really putting your tool on trial. So if there is something happen, if something happens, who's liable for the decisions that have been made? So generating explanations for the model decisions can help a user to explain his decision making. Then, yeah, so that's kind of the expert vision. So the regulator, this explanations in this case, and really needed to audit a decision trail in detail. And if something goes wrong, that's a classic example. If there is a car crash, who's the fault? Who's to be deemed as responsible? Then there are also monitoring and testing for safety standards purposes for an AI explainability analysis. And it's also at the societal level, it's also, again, about becoming comfortable with AI tool itself. So what I was saying before at the beginning of the lesson, and maybe some of you were not connected yet, I was saying that most of the development up to now for explainable AI falls in the first category, so testing for developers, and to understand how the system is working to debug it or to improve it. So there are all of these categories that still need a lot of research to be done. And digging again a bit more into this point of view about the ethical concerns and the generation of empty explanations. So I wanted to focus on these two types of goals for the interpretability analysis. So the user to feel comfortable with the prediction and keep using the system, and the deployer that is the beneficiary of the fact that giving an explanation might translate into some actions. For example, the user makes a purchase. So the deployers of a service may take benefit from either the continuous usage of the tool, or the fact that the user is making a purchase. And if, like, let's say that you have a monthly subscription to a service that recommends you songs and movies, and they decide to add empty explanations to manipulate your behavior to keep you subscribed. So an empty explanation is something that really has no meaning or foundation, but it's just given for the purpose of giving an explanation. And this is something that that was studied in this copy machine study. And this was a study, and then it evolved into a book. And it's very interesting about human behavior, because it shows a very interesting aspect of how we behave in general. So in this study, some researchers try to jump the line to make a few photocopies at a very busy copy machine at the library. And they try to do there are 3 different groups, and each of the groups tries to do a different thing. So the first group gives no explanation, and it just says, can I use the Xerox machine? The second group gives an empty explanation. So can I use the Xerox machine because I have to make some copies? And the third group provides a real explanation. So may I use the machine because I'm really in a rush? And from this study, it comes out that if you don't give a reason, the likelihood of their success was 60%. Whereas if you're giving a reason, no matter whether this is real or fake, the likelihood of completing your intent is almost the same. So this really tells you that no matter what you're saying, as long as you're saying something, this helps you to get to your goal. So even if it's illogical, that is enough to justify your behavior and to convince yourself that you have a reason. And yeah, and that's the thing, that's the risk. Saying because of something seems to work as effectively to attain compliance, even if this something has 0 information content. And this tells you a bit how also we work. Like, how many times did we say, I'm supposed to be training today, but I won't do it. I won't work out because I am so busy. It's an empty explanation. It makes no sense, but it helps you, it soothes yourself, and it makes you feel entitled to not do it. And that's really something about the human mind. And the problem with this, and some scholars have argued, is that generating an explanation, even if it's causal, is not necessarily linked to generating understanding and trust. So it's a double type of problem. On one side, you might generate an explanation that leads you to, even if it's illogical, leads you to higher confidence and leads you to higher benefits. And on the other side, you might generate an explanation that is fully causal and as hesitated as possible, and it might still not give you understanding and trust. So you see how really complicated this problem might be. And here to clarify this link I'm saying here, like, for example, if you have a patient and you give him a full causal explanation and a very high detail, technical details of a diagnosis, the patient might just not be helped at all by this. It might not improve its understanding or its trust because it doesn't have the same knowledge base, if you want, as the clinician who's giving the explanation. Whereas if you give a trustworthy account of reasons in a language that the patient understands, so it's a way in between sticking to the truth and downgrading it to some kind of level of detail that is enough for the patient to understand it, then this might help the patient to actually understand and rely on whatever the decision or the diagnosis was. And there is another problem, and here I'm listing really a lot of problems related to generating explanations. But the thing is that there's also the fact that we tend to overestimate the capacity of other people to understand what we mean. So if I asked you now to recognize a melody, if I were to tap it on the table, and I'm sure also some of you did it, like, do you remember that song that did da 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 da? Well, in that case, by asking this, you're overestimating the ability of the listener to understand whatever you're trying to say. So this might give you an illusion of transparency because you might be thinking, yeah, but I told you what it is, but the user just didn't get it. The other person just didn't get it. And then there's another point that is a connection to fairness. So let's imagine this scenario. So let's imagine a scenario where you're using a navigation tool on your phone, and this navigation tool is might do two things. Either might recommend to everyone in the same way the same shortcut to the destination. So if there were 10 users, it would send all of the 10 users to this shortcut. And this would essentially cause all of the users to crowd the shortcut, and this would probably result in taking much longer time because you have to wait in the queue to pass through the shortcut. Or like in one case, this tool might be perfectly fair and do this. Or in another case, the tool is slightly unfair, but it's unfair in a way that everyone benefits from it, because it's selecting some users, giving the shortcut to the destination to the users, to some users, and then to all the other users, it's suggesting a longer path to their destination. So you see that the tool is not fair anymore because it gives the shortcut only to some, but in this way it avoids that the shortcuts become overcrowded, so that they become overpopulated, and that there are lots of delays related to that, and everyone actually arrives to the destination in a faster way than if the tool was perfectly fair. Now, where is the fairness boundary? Like where does it fall? The thing is, if you think about randomizing the selection of users that actually get access to the shortcut, maybe randomization might be a way for fairness, and this is something that is still being discussed, and it's sort of related to interpretability and the generation of explanations, because if you were to say, like, why was I suggested the shortcut and he wasn't, then the tool might say, because in this way both of you profited from this, even if it could have been unfair. But since one of the users was chosen randomly, maybe this was fair. So that's sort of where the research is also kind of standing at the moment. So now going back, so I said a few things that I really wanted to mention, because I think it's really important to shift the attention to also the background and the context and the ethical concerns related to generating explanations, and also to the cognitive psychology insights. So in fact, generating explanation is really a complex task, and it requires considering the human involved into the task, and how the people interact with the technology, and also how people in general process information. So all of these aspects about human-computer interaction and cognitive psychology are needed to generate explanation. So one of the things that I've noticed that is needed essentially, and that I think is really needed to generate explanations that will eventually lead to a high evaluation, is the fact of focusing on applying and adapting rather than applying. So we cannot stop at applying some of the toolboxes that are available already online. The fact that there are toolboxes that are available online is great and is perfect, because it gives us as developers something that is ready and quick to get working and to start analyzing the network. But then if we really want to introduce users, if we really want to target the receiver, we need to go beyond that, and we need to consider all the different variables that enter in our application. And so, for example, in our case, how do we adapt the tools that already exist to what the physician wants and what physicians may be willing to use and can understand? So sticking to the medical application, for example, like, physicians are really the sole people that are responsible for the decision making. So there is no such thing as an AI that decides for them. They can decide to use the AI, and whenever they decide to rely on some AI toolbox, they are deciding to take in the risk that the AI toolbox may make a mistake. So whenever you talk to a clinician, what they will be telling you is like, I only use the toolbox to evaluate whether I haven't made mistakes. So if I say that there is no cancer in one of the images that I'm analyzing, I might run the toolbox to see whether it suggests that there is cancer somewhere, because I might have just overlooked it. And if it says that there is some cancer, then I will have another look at the slide. If I still don't agree with the clinician, then I might call a colleague and we might have another look at the slide together, and then we would decide together. So you really see that relying on AI toolbox is really difficult for a clinician because they are those that are responsible for the decision making. And they know that their decisions will influence the treatment planning and the life of the patient, because if you're assigned a stronger treatment, your life might also be strongly impacted by the treatment. And if you didn't need that, then this is a strong consequence. And same way in the other way around. If you needed a harsher treatment, the patient is not given the treatment that he needed, then there might be strong consequences and hard consequences. So yeah, here in my notes, I mentioned this example, for example, of imagining the impact of not needed chemotherapy because of a cancer that was strongly diagnosed as invasive. And so you can imagine what kind of mistakes clinicians want to avoid. So when they were asked, there's a study here by Tukena Boni that asked directly, it's called What Clinicians Want, and it's really, they really asked them what kind of explanations of an AI model might help you to make decisions in your daily routine. And they're asking for explanations to be appropriate to the domain. So they don't want to know high-level technical explanations that are the debugging, like at the debugging level, sorry, low-level explanations. So they don't want to know all the bits and bytes of the model. They don't want to know how the model is working and all the convolutions and all this kind of stuff. They want some explanations that reflect the way they work. And also they want explanations that lead to actions, and this is called actionability. So they need to have explanations that help them to make a decision. So it helps them to go forward. So if there is a model that is finding a cancer area and it's saying this, and the explanation might help them to understand where to go next. If there is a disagreement between what their diagnosis is and what the model is saying, the explanation might help them to understand whether they should do further analysis, they should try another modality, imaging modality, they should call like a colleague and evaluate with a colleague. So the actionability side is something that emerged from this paper, and it's strictly connected to non-redundancy. So they don't need explanations in terms of information that they already know. If I don't know, if they know, for example, that the age of the patient is not relevant for the type of diagnosis that they're doing, they do not want to have explanations in terms of the age of the patients, because they already know that is not relevant. So that's kind of the things to observe in this application. And also they care about consistency, and you will see that this is something that we'll also analyze later on in our experiments, because so explanations for a model need to be consistent. If you rerun the model, if you change the parameter initialization of your model, so if you train 5 models starting from different seeds, you need to reach more or less the same decision making, so same accuracy, and the explanations need to be the same. So they need to go beyond the simple choice of parameters and hyperparameters, because they need to reflect clinical features. So now the question became from this starting from these points, the question becomes, how do we make sure that these explanations are actually reliable and make sense for clinical practice? And how can we make these methods that already exist in the literature useful and understandable for the clinicians? And one of the points here in this slide is that using feedback is actually crucial. And this is how you enter, and this is the roadmap to adapting from simply applying. If you introduce feedback from the clinicians or from whatever whoever is the target of your explainability analysis, by collecting feedback, you manage to understand whether they actually understanding your explainability outcomes and how you can improve them to make them better. So this is really like what I wanted to say with this is that by collecting feedback, not only on the model, but also on the interpretability toolbox itself, you can manage to work on this toolbox that you have and generate better explanations and conceptual explanations. Obviously, you need to change from time to time the clinicians, because you might risk, so there is a risk in this loop, that is that of over-tuning the interpretability toolbox to your clinician. If you only have one clinician in the study, you can tweak these explanations to resemble as much as possible, and to convince as much as possible the clinician that these explanations are valid, and that's what you don't want to. So moving now to analyzing this paper and to also a more general analysis. So far that was just an idea of how to approach the problem, and now we will really see how people define and structured an evaluation for explainability analysis. Okay, so in this paper there are several tables, several visualizations, and multiple steps for evaluating your tool. The first thing is to start from is this. So it's to really understanding that generating an explanation is a process that has a feedback loop. So you need to introduce the user, you need to collect feedback, and you can see how you can improve your toolbox. But also by giving more and more information to the user, you can improve the understanding that the user has of the model. And by collecting more and more information from the users, you can improve the understanding that you have of how the user receives and understands the model and the explanation. So the user generally, whenever you're doing a user test, receives some initial instructions about the tool that he's trying to use. So there might be sometimes a little demo. There might be some introduction with some instructions, and they might have to do, like, they might be let free to use the tool for a couple of minutes. So in our case, for example, let's say that we have some tool to visualize histopathology slides at the screen. The clinicians can zoom in and zoom out. They can select regions. They can extract high-resolution images from these regions to look really at the nuclei and molecular level. And they can see the prediction of the network. So this can be the initial review of the tool. And then they can also access some explanations. So they could access, for example, some heat maps of pixel relevances and some concept-based explanation of the importance of some clinical features. I don't know, like nuclei area, nuclei texture, these kind of things. So the initial part is really to let the user free to use the tool for a few minutes, and maybe assigning some simple tasks. So try to deline an area or a contour over the image and look at what the model predicts and stuff like that. And all of this is to let the user create an initial mental model of the tool and of the model that is doing the prediction. So of your convolutional neural network or whatever deep learning method you're using. This initial instruction is then given is followed by the explanation on the model. So as I was saying, they first get acquainted to a model that is making a prediction for some data, and then they can get access to the explanation. And the explanation can be any of these explanation methods that we looked into the course. Then there are two kinds of assessment already at this point that can be done. The first assessment is called the goodness criteria, and is mostly directed to developers. So it's something that clinicians, for example, wouldn't be able to do. But developers, yes, developers might evaluate whether the explanation is clear, is precise, so it's good enough to be included into the analysis, for example. And this is sort of a priori analysis. You do this evaluation of the goodness criteria before starting the user tests. I will go later into the details, but it's really, there are two kinds of assessment that you can do at this level. And the first is involving developers, so the user type that we saw before. And the second is the test of satisfaction, and that is generally user satisfaction. So you can evaluate if the user is satisfied with the explanation, if the explanation is clear enough, and that's a posteriori analysis, because you first need to let the user use the tool, and then the user can evaluate whatever he's been using. Whereas the developer can do a priori analysis by really evaluating the tool in a stricter sense of the term. Now, these explanations that we provide revise the mental model that the users made of the model, so of the CNN or whatever architecture you're using. And this revision, you can assess how this changed. So you can record both. You see here, you can record what was the initial mental model of your user, and then you can evaluate how this mental model has changed thanks to the explanation. If the explanation has improved the comprehension of the users of the model, but then the explanation is helping, and there is a test of comprehension, and this might help. It's maybe a bit more costly and more expensive than the other tests, but it might also help you understand whether the user, for example, is able to simulate the model. And so it's understanding really at the functional level what the model is doing. And in fact, having a revised user mental model will enable the user to have a better performance. So by better performance here, I really mean to simulate better the model prediction. So if you, I think this is a bit hard to digest. So I want to go over like 1 second more on this, and then we will move on to the next points. But so let's take an example. You have a clinician, and you are using a sign method to show that the clinician, that the model has a bias. So the model is actually recognizing watermarks in an image. So you have a convolutional neural network that is trying to diagnose whether there is or there isn't a certain type of disease. And the model is actually overfitting to the presence of watermarks, because maybe there is a slice of some kind of text that says, yes, here there is the disease at the bottom of the images. And here we're not trying to evaluate the model. We're trying to evaluate explainability. So if the explanation method helps the user understand this bias that is inside the model, but then it means that the explanation model is working well. So, so the user initially may feel a bit of mistrust in this model, and it receives some initial instructions, starts using the model. It sees that in some cases, so for example, if you give an edge case where you have a negative image that has a watermark at the bottom, so you might trick your model to give a wrong prediction. So it might see that something is going on that is wrong, so it's wrong on some kind of images. And then you have a heat map that points to the watermarks, actually. So you see that this explanation is actually showing what is the problem, where is the bias. And so the user's mental model is updated, the user understands better, so he makes better performance and is able to simulate what the model is doing, and is saying, oh, there is a watermark here, I will predict that the model is going to do this. So I'm able to simulate what the model is doing, so I understand the model. So that's sort of the idea. It was a really basic example, but that's sort of what this loop is showing you. So there are some triggers and goals defined in this paper, and the thing is, the triggers are the kind of questions that users might want to ask with the explainability analysis, and they are connected to this goal. So if you have a certain purpose, then you have a certain kind of question in mind. So if you want to avoid mistake, you want to know what to do if something is if it gives a wrong classification or a wrong outcome. And so yeah, like there are also some kind of achieving understanding. So understanding what it do, and understanding what it can do, so what does it achieve, and so on and so forth. So this is all the idea of having a trigger that is a kind of question in mind and a kind of that is connected to a kind of goal. I would like to move now to the explanation goodness. So we are around here. We are in the goodness criteria here. And the first thing they're saying is that it's an a priori analysis that can be done by developers to establish the clarity and the precision of the method. So for example, this is one of the surveys that they're giving as an example, and it's The explanation helps me understand how the tool works, yes or no. The explanation of how the software works is satisfying. The explanation of how the tool works is sufficiently detailed. So here in bold are all the properties that you might check with developers about the tool. So you might see if it's actually understandable, like the outcome is understandable, if it's satisfying, if it has enough details, if it is complete, actionable, so it helps how to use the software, and also accurate or reliable, so trustworthy. These are important points. It's like I know I can really trust this explanation method. Then the user satisfaction can be evaluated with a Likert scale. So a Likert scale is generally a scale that goes from 1 to 5, 6, 7. So it's really rating things on a growing, increasing scale. But the thing is that before evaluating the user satisfaction with the tool, you need to consider that different users will be giving different scores to your tool. So it's like when professors are evaluating students at school, right? Some professors will always give higher grades than others just because they are biased towards larger numbers. So that's sort of one thing that you have to check before evaluating the satisfaction of the users. And here they're proposing a step that is a content validity ratio assessment. So you want to assess the difference among the scoring strength of different people. And this is done by, for example, asking them to score to give a score first, and then to evaluate essentially how the different classes of people, or if different people give different scores. So for example, here there are computer scientists and electrical engineer tend to give, according to this survey, according to this study, tend to give similar scores than psychologists, because psychologists tend to give higher scores than computer scientists and engineers. So that's something that they notice. So you need to keep in mind that different users might give different scores, and you can use this content validity ratio to assess the difference among people. And another thing that you can do is also to evaluate something that they call the discriminant validity of the explanation satisfaction scale. So it's just asking simple questions to your users to judge a priori what an explanation that is good would look like and an explanation that is bad would look like. So all of these are all kind of questions and prior investigations that might help you understand more things about the tool if you ask the developers, and more things about the people scoring your tool. So understanding what good means to them and what bad means to them will tell you how their scores will be placed around for your tool. Yeah. Yeah. So for example, here, like if you have like a question like how do cell phones provide directions? Some relatively bad explanations where like the phone downloads the map from the internet. So this is a bad explanation for this question. Maybe a good explanation would be the map service monitors the phone's location in real time. So at each step is given to the users based on the phone's proximity to the next step. So there are a series of checkpoints, and the user is sent to the next checkpoint from time to time. So that's sort of a good explanation. It's a clear explanation. So then after this initial evaluation of your users, then you can do the real explanation satisfaction evaluation, and that's done with the Likert scale, and it's consists of asking the users after having used the tool or while using the tool to evaluate a series of things. And you see that it's again about understanding, satisfying, like, so the parameters are the same that are assessed by the developers, but they are assessed by users now that are not necessarily developers. So they are asked whether they understand how the software works, whether the explanation is satisfying, whether there's sufficient detail, it's complete, and it's actionable. So it tells them how to use it. And they can agree strongly, be neutral, disagree strongly, and that sort of stuff. Now, the next step is evaluating the trust. So just to go back to our scale here, we have done these two, and we're now evaluating whether the trust has had any change in the user. So one way you can use, like, you can have multiple scales that ask questions related to trust directly. So do you trust the machine output? And reliance. So you trust it, so would you follow the machine's advice? And really this translates into, do you trust this diagnosis, and would you just use this diagnosis then without checking? So reliance is something very hard to achieve in medical imaging, for example. And yeah, that's what I'm saying here. So the trust scales are really specific to each application. Trust in robotics is different from trusting, I don't know, user filtering and Spotify, and medical diagnosis are, again, different. So one thing is that this way of evaluating trust, so at the end of your study, just evaluating whether they trust it and they would use it, it's a rather static evaluation of trust. Whereas trust is generally a process, so its evaluation should be repeated over time. You might have episodic measurements. So you let the users use the tool for 1 month, 2 months, 3 months, and every month you evaluate whether the trust of the user in the tool has improved. And this is a more reliable and a more dynamic evaluation of trust, and it will give you more understanding and more insights about it, because really trust is something that is built over time. So, but in any case, there are multiple ways of evaluating trust. One is with the Likert scale again, so asking about the confidence and predictable actions, reliability, do you think it's safe? So all of these type of questions that are reported in the paper are also expressed on the Likert scale. So from trusting it to not trusting it, with different shades. But there could also be other scales. So for example, there could be this one that is saying choose an option in terms of reliability. And there is, okay, always provides the advice, performs in a reliable way, responds the same way under the same conditions at different times. So this is also a scale of reliability. Maybe it's a slightly different answer than this. So it's not saying, okay, I know that it performs in a reliable way. Here it's saying, well, I tested at different times and it performs in the same way. So there's still some hints that it's less strong than the one before, and so on and so forth with different shades. And I think that there are some users that might be more inclined to using this, and others that might be more inclined to use this. Yeah, and before going to the more technical evaluation from the developer side, I wanted to maybe jump back to the slides, and I apologize for this, I should have repeated this multiple times, but jumping back to the slides and moving on to the tests of comprehension and performance that are also reported in the paper and I'm not mentioning in the talk, because otherwise we will stay here until midnight. But there are a couple more things that could be insightful when you're working with users. So one of the things is really understanding their level of understanding. It's trying to record and to document the level of understanding of the user that the user says of the tool. So, for example, asking the user to think aloud, to talk while using the tool, saying whatever he's thinking of the model and how he thinks the model is behaving. So that's sort of a way of recording really with transcripts whatever is passing in the user's mind and that is informative about the mental model that the user is making. And that's sort of an analysis that you can do to a few users, for a few users, to really see whatever is their kind of understanding of the model. And then there are other papers and the that focus on the test of performance from the user side. So they take inspiration from the fact that if you do not know how to do something yourself, then you don't understand how it's working. And if you do not know how to explain something to a 5-year-old kid, then you don't know how the system is working, the thing is working. So there can be this test of performance being like, okay, first thing is user simulability. So can you simulate the model behavior? So can you do the same functional output as the model? If I give you this input, what will the model do? And the second is user the paraphrasing of whatever the model is doing from the side of the user. So trying to explain it in simple terms. And that's also a test that can be done to see how well the user is understanding the model. So moving to some evaluation examples, the first part is really a technical evaluation by the developers. And there are also some studies about this. And here I'm referencing to two that I think were very important in the research panorama. So the first was by Kindermans in 2017, where they really they evaluated the reliability of saliency methods. So you have a heat map essentially that is showing you the relevant input features, and they were assuming that the explanation should be invariant to the input, to constant input shifts. So if you have an input here and you apply a constant shift, that is, for example, this here they did some like pixel values shaped like a cat, so they're really trying to trick the attribution method. And this is like just adding. You take your image, and whatever image you choose, you add some pixels to it and some pixel values. This is a constant shift. And if this is still classified as a 7, and that's something to check. So if this shift does not change the model output, but then the explanation should be the same. This is a 7 because I've looked at the shape of the 7. And actually what they observed in this paper is that this is still classified correctly as a 7, but the explanation changes. It says this is a 7 because there are also some pixels around here. So you see that this is really a failure of the attribution method because it's not invariant to constant input shift that do not change the final decision of the network. And it's weird, you know, to have something that does not affect the output, but largely affect the explanations. It's telling you that something is not working as expected, and so this was the essence of their point in the paper. And this was then followed up by some more studies about sanity checks for saliency maps. So they took a bunch of saliency methods, most of, like all of them gradient-based methods, I think. And what they evaluated is they evaluated two things. The first thing was a parameter randomization test, and the second thing was a data randomization test. So in this image here, I'm showing the parameter randomization test, where cascading randomization of the model parameters is done. So here you have your original explanation. So the model is being trained on ImageNet images, and it's an Inception v3, and it's been trained to classify the classes in the scene set, and it's working as well as the state-of-the-art Inception v3. And you have the original explanation. So you have what, according to the saliency maps, this model is looking at. But then if you take the logits and you perturbate the values of those weights, you generate the explanation, and you see that the model performance, when you perturb the logits, it goes to random because you're just screwing the weights that were learned to make the classification work. So if these images are showing you what's being used to make the classification, well, if the classification is not working anymore, these images shouldn't tell you something very informative. They should tell you, well, I don't know, because the explanation is the output is wrong. And if you keep randomizing all the way to the top, you still see that some of the explanations remain quite unchanged until the very end. So this is showing that these saliency methods are maybe strongly biased towards something else. And in the paper, they're assuming that they are strongly biased to behave as edge detectors. So I'll let you read the paper if you want more insights, but it's a kind of test that can be helpful when you're working with gradient-based approaches to evaluate whether your analysis is still reliable or not. And in this case, if you see like GradCam, for example, well, after the randomization, it's working because, okay, it's slightly similar here, but you see that then as you start randomizing really the internal activations, it goes completely to random. So that's good. In this case, a guided backpropagation, this is really bad because it really says that, well, no matter what you're passing me, I will still point to something that looks like at the edges. And when you look only at this with a qualitative assessment, you're biased by confirmation bias to think that, oh yeah, it's recognizing the image because it's looking around here and it's looking at the eye. Well, no, maybe no. That's sort of what the explanation, the evaluation of the explanation is useful for. And now I would like maybe to move 1 second to the medical application and to our work. So we also proposed a technical evaluation of post-hoc visualization methods for histopathology. So we had an inception V3 similar to the papers before, but this inception was fine-tuned to solve a binary classification task on histopathology images that look like this, to recognize the presence or absence of tumor in these images. And we took the most cited visualization methods that had an intuitive application to these images. So we took class activation mapping and all the different variations of it, and local. So Lime. Lime is, as I was mentioning before, is a generalization. It's one specification of SHAP values, and it's a model agnostic method that evaluates feature importances by perturbation. So it selects some features by superpixel. So it finds superpixels in the image, and it removes the superpixels randomly, and it evaluates the importance of each superpixels by looking at the output when you have this perturbation of the images. And yeah, so we took these methods, and we decided to evaluate how these methods were corresponding to the criteria that I introduced before, to evaluate whether the explanation is giving to the clinicians what they want. So if it's giving anything that is appropriate to the domain, if the explanations agree, so if there's no redundant information, and if the explanations are consistent and reliable. And this is what we find out. So the first thing we did was to evaluate whether the explanations agreed. So we took these methods, and we evaluate the similarity between the images generated for these methods on the entire dataset. So we run explanations. We run the inference pass for the model for all the images, and then we run all the explanation and all the explanation methods for all of the images. And we computed the pairwise similarity between the methods. And so here you have the couple of CAM and GradCam, and as you shouldn't be surprised if you followed lecture 2, I hope so, but this is expected. So CAM and GradCam have a very high similarity, and that's correct, because GradCam is a generalization of CAM, and it acts as CAM up to a normalization constant. So that's good. What is less good is that all the other methods do not agree on the true positives. So their agreement rate is really low when they're predicting tumor. So this is confusing because if they're predicting tumor, it means that there is tumor in the image, so they should be more or less pointing to the same region. And this is showing that no, they're not. So that's the first thing we noticed. Then the second thing we noticed is we evaluated the attention of the network to specific nucleotypes. So for the input images, we had contours annotations of different nucleotypes. So for example, of neoplastic nuclei that are nuclei that present morphology variations. So they are tumorous nuclei, or they might highlight the presence of tumor. And then other types of nuclei that are inflammatory, connective, or epithelial nuclei that do not show any presence of tumor and are not correlated to the presence of tumor. And what we did was we evaluated the intersection of a union of the different types with the heat map, the explanation heat map that we get. So if the intersection of a union was defined by in the paper of network dissection. I mentioned this in some of the lectures, and it's essentially evaluating if you take two contoured regions, you take the intersection and you compute the fraction of the intersection over the union. So you really evaluate whether these two areas overlap. And we did this for each of these nucleotypes. And what we're showing here is that the intersection of a union is higher for neoplastic nuclei than for all the other types. So then we thought, okay, this is a good sign because it means that the network is really looking at the neoplastic nuclei. Now that's one thing. Then the second thing is that you need to be very critical when you're evaluating your explainability method. So even if it's showing something that you think makes sense, you might still want to test it again to evaluate whether you're falling into a confirmation bias risk. And so we did another test. We said, okay, we have our training network. Let's compare these to the complete randomization of the network parameters. And that links to the paper that I've mentioned before with the cascading randomization. So if I take my network parameters and I randomize all of those, is my intersection of a union still higher on the neoplastic nuclei? Because if so, but then it means that just maybe there are more neoplastic nuclei in my image, and that's why their intersection of a union is higher. Maybe it's just because there is a bias in the data. And in fact, that was the case. So essentially, if we compare the trained to a random network, there is no significant difference in the intersection of a union for these two classes. So that was another result that we evaluated that told us, okay, so maybe these heat maps seem to be pointing at neoplastic nuclei, so at tumorous nuclei in the image. And if we look at them really from qualitative evaluation only, we do see that. So if I take an image with tumor inside and I show the heat map, well, the image is pointing to a tumorous nuclei, but it's maybe not that statistically relevant because maybe there are just many tumorous nuclei in the image, and the heat map is also falling in there. So that's something to consider and to be careful with. And then the third thing we evaluated was the sensitivity to hyperparameter changes. So there are some explanation techniques that require some hyperparameter tuning, and SHAP and LIME are one of those. So you can do these tests at any moment in your analysis. So you can start with LIME with the default parameters, and then you can generate your explanations, and then you can see how much your explanations are impacted by varying the hyperparameters. And that's what we did, essentially. There are two main hyperparameters to set in LIME. One is how many superpixels you're considering for your analysis, so how many features are you perturbing, essentially. And here's your neighborhood size, so it's how many images are you considering to find your explanation. And you see that there is a very so you need a fair enough number of superpixels to become constant, but even a larger neighborhood size. So you need a large number of images to get something that is consistent. So this is the first observation that we did by doing this evaluation. And then the second thing was, okay, so, well, I will get now my best hyperparameter values from this research that I did, and I want to check the repeatability. So there is an initialization seed for this technique that you need to specify. And what we tested was, okay, if I change the seed every time, do I still get consistent results? And to get consistent results, you need a low number of superpixels, and this goes against this. So you see that you get consistent results in terms of repeatability, because you get maybe always the same area of firing, but just because you have less pixels to choose from. So if you have an image and you have 10 regions and you want to evaluate how the explanations are consistent, choosing from 10 regions has a smaller variability than choosing from 100 or 1,000 or 10,000. So that's sort of what we evaluated here, and it's showing you that this method is very unstable to initialization of a seed, so it's not repeatable, so the explanations will always be different. And if you want them to be consistent, you should use a number of superpixels and fix the seed. But then, I mean, it also tells you the limitations of the methods itself. Like it's limited to this configuration. Yeah. So then another thing that I wanted to mention was some preliminary work that we're doing with the user evaluation. So as you've seen from the long introduction and from all the slides before, it's quite complex to work with users, but our goal is really to introduce physicians in the loop. And the first thing we did was to just run a Google survey on a few visualization examples. And that was already really helpful. So we took some images like this with the model prediction. So here there is a tumor cell, like there's a cell that looks slightly weird because the nuclei is really big, and the texture here is weird. And I would say that also this one is a weird nuclei, and I mean, is a weird cell, and this one too. These two also look weird. So that's sort of what I can say. I'm not a pathologist, I'm a computer scientist, so I learned this from experience, but I might be saying something wrong, but that's how I feel about this image. And we have a model prediction that is saying, yeah, this could contain tumor because the prediction is rather high. And so then we proposed them with some revised version of Lime that is taking into account the shape of the nuclei, and it's saying, okay, this was relevant to the prediction because it's high activation value when it's blue, and the red is low activation value. So this is not as relevant as this one. This one is not as relevant, but it's still relevant, much more relevant than any information included in the background. So we presented them with this kind of explanation, and we presented them with also the classic GradCam that shows that the cam is looking somehow in this region up here, a bit around here, and a bit around here. And we gave them a Likert scale and like asking whether these visualizations were helpful or not. And we also let them just answer openly to some questions. So they could just write text, and we also had some interviews with some of them to try to understand how did they feel with this kind of explanations. And one of the things that came out, there is an interesting observation that I would like to use to close really this presentation about the evaluation, the evaluation of interpretability method, is that even asking such simple questions to the users can point you to some fundamental problems about the research that you're doing. So for example, in this case, some of the people said that these images were difficult to understand, and the explanations and also the outcomes of this. So these two methods had really no meaning to them because the image fragments were way too small. And they're saying also these examples bring cases down to cytology. Well, I'm a histologist, so it is not about the nuclei, but more about the context, and that is what Lime does not provide. So these images do not provide any information about what's around the image, essentially, because we cropped it, and we cropped it because that's how the network is working. So you see that there is a lost in translation problem. Because deep learning models for histopathology, for example, tend to operate on very small input sizes. So they work with this kind of image size. They look at these images assuming that they are independent. So we can only generate explanation for what the model is looking at and for how the model is working at that point. We cannot generate explanations that would correspond to how a pathologist works directly, because we can only explain what the model is doing, and we cannot generate extra information because we need to explain what the model is doing. So you see that there is a loss in translation problem, because what the network sees might not directly correspond to the way a pathologist works, and so there is a kind of gap that still needs to be addressed. And that was my last slide for this deck. And so I don't know what time is it? It's 5:20. I hope there is still some time for question and answers. So maybe we have a few minutes, like 5 minutes or a bit more for question and answers, if any of you has something to ask. I will stop sharing the screen.
Maybe, so in this last example that you showed, so I understood the problem is that you are feeding patches and not the entire images.
Yeah.
And that's the same thing that I'm doing for the aneurysms. But in the end, I can reconstruct the whole volume segmentation. Can't you do that? Couldn't you do that?
Yeah, so there is a paper that does that. It's a paper by Samek and Mueller, I think. So they run LRP and GradCam for histopathology images, and they extracting patches. They have these heat maps, and then they just take the heat maps and they put them one next to the other.
They merge them, yeah.
Yeah, but you see that is, again, not how the network is working, because the network is assuming that those images are independent samples. Yeah. The network doesn't know that there's context around. So either you change your network or you're limited to that kind of. So that's my stopping point at the moment.
Yeah.
Yeah. So that's something I wanted to point to, as it's not as correct. I mean, it could. Creating this puzzle of explanations and heat maps might give you something that looks good, but is it really telling you how the model is working? No. Is it really explaining? That's sort of the things, the small subtleties in generating explanations that one needs to be careful to.
Okay.
Mara, Sean here. Yeah. I'm just curious, when you obviously, in many cases there, you had the physicians would look at it and say, no, that doesn't help me. Did you find in any situations where they started looking at the images differently themselves after they saw how an AI had interpreted it? Did it change in any way the way they operated?
So as far as my experience goes, what I've noticed is that several times this first happens with developers. So to us developers of the model, we're sure that the model is doing something, and then we start looking at these heat maps, and well, we change our perception about what the model is doing, and that's when we're debugging essentially. So, for example, one of the things is we had a model once that was predicting colorectal cancer, I think, and then we found out that the model wasn't actually looking at any area of the colorectal cancer. Whereas, so that was really a problem in the model. Whereas another thing that we've seen is that if they're asked to choose between something that has a bit more details and a bit more structure, so that looks more like at the cell contours, for example, and that discriminates between cells, so cell relative importances, it seems that it's preferable to have something like that rather than to have a diffused heat map that is not very, very clear. That's the problem in histopathology, is that you have multiple instances of the same thing, and if you generate just a heat map, it can be very diffused and it might not point at each of these instances. So by putting some prior knowledge, you can reshape the explanations into something that is closer to how pathologists might work. And some of them replied like this, but others replied that they, so let me just put again 1 second, because otherwise it's difficult to follow. So some of the people here replied like this, that this algorithm has no meaning, that they don't know, and that is doesn't really align with how they work. But others said, well, actually, this is more understandable to me than this one. I prefer to have something like this. So that's also like a start.
And is there any way for almost like a double-blind way of looking at this, where you would say to the pathologist or whoever the clinician is, can you mark where what you think is telling you is or is not, an example of the positive case, and then see if what they mark matches what your AI has interpreted it?
Yeah, definitely. That's a good point, and I think there's so much research to do in this field. Like, and one of the things is from Jenny's lecture. I don't know if you followed it. It was
I did, and I have a feeling that's where the idea has popped into my head, because I think she did something similar to that idea.
Exactly.
Yeah.
I think that was great. I mean, they can take, like, you can use an eye tracking device and check where the clinician is looking and see if it overlaps with what your explanation is pointing to, and that might be telling something more. But I don't have any collection of work doing this, so if you find it, please send it to me. I would be very happy to read about it. But that's a good point.
Though that also that the clinicians find it hard to explain themselves. I mean, humans are not that interpretable either, I suppose, and it's very difficult for them to say why they're decompose it down.
Yeah, absolutely. Like, I haven't given a broad overview about the problem of histopathology, but one of the first things is that there is high disagreement among clinicians. They don't agree about the diagnosis. It's the agreement rate is really low on these images, and that's a bit scary. But it seems that using deep learning helps them improve their agreement rate. So there is a bunch of things that can be developed to help them, for example, look at the same things, avoid overlooking other regions, and avoid making these kind of mistakes. And that already improves the performance of the clinician. So by merging the two of them, you can really get to higher performance rates. But this is a first step, but then the second step is that the clinician needs to be motivated to use the software, needs to trust the software. And if there is not this link between user and trust in the method, then okay, you might have a study that tells you, yes, combining deep learning and clinicians really reduces the error rates, makes them drop significantly. But then are they actually ready? Are people ready? Do we have enough to introduce them in the entire, like in the diagnosis pipeline, in clinical routines of every day? What is missing? And that's the kind of things that are missing, I think.
Sure. And do you find that the clinicians are more likely to obviously there's that kind of there's often an attitude that they're right, and that if another person comes in and says something different, that other person must be wrong. Whereas if an AI comes in and says it, that they might be that they don't feel as threatened by it, I assume.
Well, I mean, we did some more of these studies, and I don't have the slides in here, but
Sure.
they do they are very open-minded. So you really see whenever they choose and say what the action would be if there is a disagreement, it's really about, like, I mean, they're not very proud. I mean, what they care the most about is to give a correct diagnosis, or to make the diagnosis as correct as possible, because really they have the health of the patient in mind. So if there is disagreement, they would maybe ask another person, they would maybe ask a colleague, or they would use the AI, for example, on all the negative cases. So if they see a slide and they say, here, there's no cancer, well, maybe they would use the AI just to check if there's some area that needs a second look. And they wouldn't mind giving a second, a third, or a fourth look to a slide, just to make sure that they're giving a correct decision. So that's sort of the behavior, I think. It's more like, if there is an area that is uncertain, well, we dig more, we check more, we control more, we take more time.
Well, that certainly suggests then that they would be quite open to seeing what an AI comes up with as well, which is good, that they're at least open to it. Yeah.
Yes, absolutely. They're very open to it. And also there are many tools that would probably help the diagnosis. Like in some cases, there might be, like, if an area is uncertain, they might just require for a different image modality, So there are some image modalities that are more expensive than others, and they're more difficult, or they're not as easy to obtain. And there could be AI tools that fill in for that. So, for example, changing the image from one staining type to another. And I won't go into details, but you really notice visible differences in between the images. They look completely different, and they tell you much more. And there are papers that are training AI, like deep learning models, to simulate this.
Very good. Thanks.
I don't. I'll stop sharing screen again. Okay, so I hope that you found the course interesting, and I will also share the recording of this class on the web page, and so that you can follow again things. And you can also keep contacting me if you try one of the notebooks or one of the Colab notebooks for your application. You can contact me if there are problems or if you want some help or something. But yeah, that was cool. I will maybe send you at some point I mean, if you could give us feedback on the course, that'd be great, because if we're planning on running it again, we might consider some feedback to make it better. But yeah, I hope you found this interesting.
It was great. Thank you very much, Mara.
Yeah, really nice.
Okay.
Very nice lecture.
Yes.
Yeah,
anyway,
I might be contacting you soonish, because so we are applying now this Lime for the reports, but I also don't want to. I mean, it's already 5:30, and I don't want to keep everybody online. But yeah, I have 2 or 3 questions if you want, if you have time. And
feel free to write me. Yeah, I'm very curious. So feel free to write me
cool.
if you're trying to apply it.
Cool.
Okay.
Thanks a lot.
So then I will maybe let you all go, and thank you so much for attending. And yeah, let's keep in touch.
Thank you. Take care.
Bye.
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 Thanks, Mara.
Bye. Bye. Have a good day.